only thing is that he had a glass after us, he was not a glass. He would stand outside on the window, you know, like the house has the big windows and and he stares in, like really spooky, you know, like and then when we get out, he opens the door for us and the way he gets us place, you know.
Okay, let's begin. It's my privilege to welcome you to the University of Tennessee Nuclear Engineering Department Seminar Series. Today's speaker is Dr. Martin McBride. Martin has been involved in the nuclear business for over 25 years. He has an undergraduate degree in physics and an advanced degree in bionucleonics from Purdue University. He has run a commercial nuclear medicine research laboratory. He's worked for a nuclear power utility and was a senior inspector for the NRC. After joining DOE, he headed restart teams for the high-flux isotope reactor at Oak Ridge and for plutonium operations at the Rocky Flat site. He is currently the Director of Nuclear Safety for the DOE Oak Ridge Operations Office. Today's topic is the next safety breakthrough. How do we get there? Dr. McBride, welcome.
Thank you very much, Professor Dodds. What I'd like to talk about today are some ideas that I have developed over the last few years as I have traveled through the nuclear industry. I've been involved in a number of different activities from both the commercial side, from the regulatory side, and from the Department of Energy side. And it has impressed me very much, the cycles that our business, the nuclear business, has been through over the last 20 years. One of the things that has intrigued me is the question about safety improvement. Safety improvement has often been the watchword in the nuclear industry, and it has been something that has often come in spurts and through fairly traumatic financial impacts on things like nuclear utilities and in the Department of Energy. Some of you may be aware that in the late 1980s and early 1990s, virtually the entire Department of Energy nuclear complex was shut down forcibly as we went through a series of safety upgrades. The question was that has been in my mind is we know how to improve safety in our plants. We know how to improve safety that has to do with hazardous work. Do we need to find better ways to do this improvement? Now, as I'm talking about safety improvement, I'd like to put our focus on this group of three characteristics, not just safer work performance, but also safer and faster and less expensive work performance. One of the questions I ask is, do we need a breakthrough in safety in the future to support our nuclear industry? As our nuclear industry moves forward, can we flourish? Can we even survive long term if we don't have significant improvement in how we do safety improvement? In looking at the answer to this type of question, looking for the answer to this type of question, one of the first things I think you need to do is think about what are people's expectations for safety likely to do in the future. As you travel around the nuclear business, a lot of people end up asking you the question, well, how much is enough? How do I know when I've spent enough on safety controls? How do I know when I have enough procedures? I have enough training of my workforce? These are very important questions. First part of that is, well, what do people expect? And I think what this slide tries to show is over the last couple of 100 years, the trend has been in one direction. It's been up. And I think that is primarily because when you talk about significant safety events, you're talking about things that involve human tragedy. You talk about death and severe injury, whether it's happened today or 50 years ago or 150 years ago, it's still a human tragedy. And so I think my guess is that kind of driver will continue to drive our safety expectations higher and higher. Another observation that I made is that even today, we seem to require precursor events before we conduct significant safety upgrades. Would major improvements have occurred in nuclear safety without the 3 Mile Island accident, the Chernobyl disaster, in the Department of Energy? Would we have gone through significant, and again, I'm talking about significant safety upgrades without the almost total shutdown of the nuclear complex in the late 1980s? Last week, I was in Washington talking to a group of people on chemical safety, making a very similar point in chemical safety. The Bhopal tragedy in India killed thousands of people, seriously injured more. That had a traumatic shock effect on people and drove a lot of chemical safety improvement. An interesting question, is there a way to get that kind of improvement without having those kind of tragedies precede them? Now I thought I'd throw this example, the bottom in. All of us, I think, can relate to the increased airline security that's going on now. Some of us can remember the time when it was easy to just walk down the jetway and get on an airplane without any kind of security controls at all. That was pre-hijackings of the 70s. Then we went through a period of increased security protection, and now we're all seeing a further step change increase. Significant changes. Wouldn't it have been wonderful if we could have figured out how to kind of ramp up security and avoid some of these catastrophic events? Dr. James Reason, a British psychologist, wrote a fascinating book in the late 1990s called Managing the Risks of Organizational Accidents. Fascinating from the fact that Dr. Reason works with a wide variety of industries, including the nuclear industry. And he has a number of insights into how organizations tend to cause accidents. And one of the things that I saw in his book, and that I adopted, and I've christened Dr. Reason's curve, is this little chart here that shows increasing safety protection on this axis and continuation of time, or Dr. Reason put increasing levels of production, I put increasing levels of time on that axis, to kind of show the step change improvement pattern. It's a sawtooth. It's not continuous. And the idea here is you go along thinking you're doing great. You have some kind of safety event. You get a reaction. Your safety protection controls increase in a near vertical manner and hopefully do not drive you up into the bankruptcy zone. Then you reach a point and people think you've improved enough. You continue on further. Chances are you tend to slack off a little bit. Meanwhile, with time, protection expectations are increasing, and you run into another safety event, jacks your protection levels up, your costs up, and you bump into this bankruptcy curve. If you're unfortunate enough, your costs go so high you cannot afford to stay in business. If you're fortunate enough, you stay in the improvement zone and you continue on. I think we see that pattern over and over in a number of our hazard-based technology businesses, of which nuclear is one of them. And of course, this raises the interesting question, Jesus, this is as good as it gets. Is there a way to crack through something like this and maybe even this thing out so you don't take the risk of bankruptcy with you as you, and obviously you prevent the events. Now, one of the things that Reason's curve brings you into focus with is what happens when you have your next big event. Reason's curve suggests that there's going to be another event that's likely to happen in the future. Most of us don't tend to think about that we're focused on many other things. In the nuclear business, we've had our past events. We've had our 3 Mile Islands and our Chernobyls. We've seen a dramatic step change increase, and I've been there, and it was dramatic, the increase in safety protection that happened in the nuclear business after those circumstances. What's happening now? We've got another generation of reactors, nuclear technology on the horizon, which I'm personally enthused about. I think it's really neat. I'm a nuclear technology enthusiast. But I also believe that society's expectations for protection are increasing. They're going to continue to go up. So, is this going to happen? The next big event? And if it does, what effect is it going to have on our industry? Another thing that Dr. Reason has in his book that I was fascinated by is this little chart, or a version that I turned into this little chart. He made the observation that what typically happens when you have these events is you go in and you engineer in additional layers of safety control, and they get stacked on top of each other. Now, in this chart, and this may be a bit confusing, but the white area here is the level of freedom that people enjoy, the workforce enjoys, to get its job done in what it sees as the most efficient, fastest way it can get the job done. As time goes on, you have an event, you layer on another layer of safety control, and their freedom of movement decreases. Another event, it decreases further. We don't tend to take away these other layers with time, we leave them in place. So after a while, this thing kind of necks down to a very limited area of freedom, which if people were robots would be not a problem at all. But since we're thinking, feeling human beings, we tend to generate all kinds of creative ideas when people feel that the process is kind of working against them and they can't get their job done. And that's when you begin to have things that creep in where people start short-circuiting safety controls, start finding other ways to get the job done. All kinds of interesting things start happening when this layering reaches a point that it becomes too narrow compared to what the folks need to get the operational flexibility they need to get their jobs done. That's reality. That happens. So those are some aspects of trying to answer the question, do we need another safety breakthrough? What is the safety expectations going to do? And what's happening right now with safety controls? Another part of that question, I think, has to do with, well, so why are we worried about this type of technology in the first place? This chart tries to get at make the point that there's an awful lot of people in the world that can't afford the kind of safety protection we can afford. I was kind of shocked when I put this together and recognized 3.5 billion people around the world right now live in economies where the average per capita income is only $500 a year. Those folks cannot afford our modern hazard-based technologies and all the benefits it brings. So to the extent that safety costs contribute to the overall cost of our technology, if we can become faster and less costly while meeting people's safety expectations, we can start making a contribution that goes beyond our immediate needs. Safety breakthroughs, substantially improving safety while making work faster and less costly, boy, that's a nice idea. Tempting. Question is, how do you do it? Not an easy thing to do, at least in my opinion. We're very good at what we do now, but if we talk about raising the bar significantly, not just getting a little bit better and getting a whole bunch better, how do you do that? Well, one of the things we need to think about is, where do we look for this improvement? Traditionally, we have looked in engineering solutions, technology-based solutions to this. I think there's a bunch of breakthroughs to be found having to do with people-related issues. But they're very complex, and you have to get into things that deal with decision-making. And in our nuclear business, there has to be a tie between the decision-making and the engineering decisions that we make, the technology we choose to employ. As an example of the factors that I think would be very interesting to study and understand, the Department of Energy ended up spending billions of dollars of precious taxpayer money to upgrade its facilities in the late 1980s and early 1990s, its nuclear facilities, because we had fallen seriously behind society's expectations for nuclear safety protection. That's a lot of money. One of the questions I have, and I've read a lot of studies about those issues, those problems, those fixes, what fundamentally caused the department to get in that kind of fix? You can ask the same question about some of the other major accidents. Some of you may have read about the Challenger space shuttle accident. What ultimately caused that accident is a question. You'll see things about the engineering failures, the O-rings, in that example, for example. And you'll read stuff about how people made decisions as to whether to go ahead or not. You'll read about how some information was not passed to some of the decision makers. That's all very interesting. But what's driving a lot of those organizational decisions? I don't think we understand those issues very well at the current time, which translates into, in my view, a real opportunity for us. I think these are areas we can really delve into, gold mines for us of potential advancement. Another area that's interesting is personal accountability. Now, one of the things that's fascinating to me, well, I work in an industry that places a very high value on personal accountability. Part of it comes from the Navy, the nuclear Navy influence on our nuclear business, and I think it's neat. When you get into the federal service, however, I can tell you that there are many, many limitations on us bureaucrats that keep us bureaucrats from being held accountable for certain things. Accountability? What? I don't think so. Accountability motivates us. It makes us perform. By accountability, I don't mean the typical accountability that you see where well, that person's at fault for this, therefore we need to exact some kind of punishment. I'm talking about accountability where people understand what's expected of them. They think they get excited and think they can achieve it, and then there are consequences for whether they achieve it or not. Those kinds of systems where the positive accountability systems that help people get their work done, you end up getting tremendous results. Right now, there are a number of areas in the Department of Energy that we could look at. It's a fascinating test bed for those ideas. One of the things that I talk to people about as I talk to breakthroughs is, hey, has anybody else thought about breakthroughs as part of a corporate strategy? I said, yeah, as a matter of fact, look at the computer on your desktop. One of the reasons you got that thing there is because back in the early part of the last century, a corporation was thinking about breakthroughs. Let's consider the sad case of poor AT&T in 1907. At that point, they were in a very difficult situation. All of Alexander Graham Bell's patents were expiring. That means their lock on the telephone business in the country was about to go away. What do? Telephone service at that point was all local. You couldn't make any long-distance calls because there was no practical electrical amplifier system. And boy, you better believe the competitors were out there. And they were licking their chops, just waiting for the patents to run their course, and then they were going to swoop in, and AT&T, former glory days were going to be a thing of the past. So they thought about, well, what do we do? I don't know what I would do in that situation. What they decided to do is go talk to a former president of their company that had retired and say, boss, what do we do? And he said, in essence, go find yourself a breakthrough. They did. They talked to a guy named Lee DeForest, who had come up with this contraption, part of it's left off the screen here, the vacuum tube. Vacuum tube was a wonderful invention. AT&T took it, perfected it, engineered it, and used it as the basis for long-distance telephone service in the in the country. They slam-dunked their competitors, established a whole new battery of patents, and the rest, as they say, was history. Doesn't stop there. 4 decades later, at Bell Labs, while a bunch of other people were thinking about, well, how do I build a better vacuum tube, a guy named Mervyn Kelly was thinking, now wait a minute, how do I break through the performance limits that a vacuum tube gives me? You know, a vacuum tube puts out a lot of heat, takes an awful lot of power to run it, and it's not very reliable. A bunch of people said, yeah, well, all you have to do is re-engineer this a little bit here and there and modify, and you'll end up with a better vacuum tube. He said, I want to try something with this strange new set of materials called semiconductors. So in 1945, he created a research team. He had the advantage that he happened to be the head of Bell Labs at that point, so he could do those kind of things. Fascinating group of people he brought together. If you ever get a chance to read about them, they make great reading. A bunch of very brilliant people who had very large egos. They got together, promptly clashed, named themselves Hell's Bells Laboratory, and failed, which is what often happens when you start with breakthrough pioneering research. You very rarely get it right the first time. But they kept at it, and as I said, they were really a brilliant group of people. In 1948, they introduced the transistor. The transistor smashed the previous performance limits, and that's why it's a great example of a breakthrough. It didn't just do a little bit better than a vacuum tube. It did a whole lot better than a vacuum tube. Then the next breakthrough that happened after that actually was occurred because of some disciples of the original research team in the 1940s that had migrated to other companies, Texas Instruments and Fairchild Semiconductor, and in 1958 the microchip was born. Now I want to switch gears for a minute. We've talked about breakthroughs, what breakthroughs are in terms of magnitude of change. I want to talk just for a moment about the Department of Energy's Integrated Safety Management Program. This is a set of conceptual ideas that were introduced about 6 years ago. The ideas were originally developed by our regulatory, well, non-regulatory, but our oversight board, Defense Nuclear Facility Safety Board, in what I think is really a very good, a pioneering conceptual model. Many of our safety models that we use in the nuclear business go back to engineering models. Defense in depth is something you'll hear often used as we design our systems. You hear people try to adapt that engineering model to people-based systems, training systems, whether you have procedures or not, that kind of thing doesn't work very good. You can make those engineering models fit people and fit people issues, but it's kind of a forced fit. This went in a different manner. This said, how do we get hazardous work done? These are what they call the 5 core functions. It's kind of elementary, I'll grant you, but it is a real nice way of thinking about how you do hazardous work. Define the work scope, analyze the hazards, develop your controls, and so forth. In our processes and policies, we have a whole bunch more discussion and description about what these things mean. The same reason I'm putting this up here is until you have a fundamental conceptual model, it's hard to build something better. This is a wonderful candidate for our foundation model. One of the other aspects of this model that I thought was really interesting when it came out, and I was privileged to be at the public hearing back in 1995, I guess it was, when this was originally discussed. And I thought, geez, this is terrific. We could build an awful lot on this thing. In part because some of its principles, which are the background in which you do work, involve cost. And in safety, people-based safety, often there's a big gulf between safety control and how much it costs. This one conceptual model starts bringing it together, just like Reason's curve did. Remember, they had the section on Reason's curve that was catastrophe area, section that was the bankruptcy area. This model does the same thing. It also forges a conceptual link between three important strategies in safety management. There's one strategy that's out there that focuses on the individual. The individual should do a good job, should be motivated, should be accountable as an individual. There's certain strategies that focus on that. There are certain strategies that deal with engineering, the human interface. These things have to do with a basic human factors engineering. And then there's some strategies, like Dr. Reason's that he was introducing, that says, no, wait a minute, there's other factors here. The organization influences things, organizational decision-making. ISM brings all of those together. However, just like the vacuum tube, ISM has inherent performance limits. And I'm going to talk about one of them here. We've already talked about Dr. Reason's curve, the fact that we seem to still need significant safety events before we take significant safety improvement. This one, I'll let you read about in my paper. If you're interested, it has to do with the relation between safety decision-making and certain other types of decision-making. This one I thought was kind of interesting because if you think about our principles that we have in ISM, a lot of them don't involve numbers. They don't have much to do with quantitative relationships. They don't have much to do with what we typically think of dealing with in engineering. They're axioms. Axioms are self-evident truths. We use them all the time in human knowledge. And by axioms here, I'm not talking about mathematical axioms. I'm talking about the more generic definition of axioms. Self-evident truths. People ought to be responsible for the safety outcome of their operation. That makes sense to a lot of people. It makes sense to me. It's an axiom. It's self-evident. So what's the problem? Well, one of the problems with axioms is, while they're very useful, we use them all the time, in part because we don't have the money or the time to scientifically prove everything. Axioms are slow to change because they're self-evident. How do you change truth? It's truth. They're often vague. And they're sometimes used as political decrees, which typically in our culture generates a reaction like, oh yeah, you want me to do that? Well, just try and make me. Which in turn means you got to spend more money and your costs go up and so forth. Dr. Richard Feynman, who is another one of my personal heroes. I enjoy reading about him. He was a real character. He was involved with the Manhattan Project in a major way and a Nobel Prize winner. He wrote a little book called The Character of Physical Law. And in it, he talked about people who talk about things they call science, but he didn't believe it was science. So he tried to explain what the difference was. And it's this. This is a lot of words. I apologize for it, but if you just take a quick look at what's highlighted here, the possibility of proving a definite theory wrong, there's always that possibility, but we can never prove it right. That's what science is. You can never prove something right in science. Suppose you invent a good guess, calculate the consequences, and discover every time that the consequences you've calculated agree with your experiments. The theory is then right? Nope. You just simply have not proved it wrong. I look out my window. I see a car passing. It's a Buick and it's red. I make a hypothesis. All Buicks are red. I get out of the street, watch the traffic for a while. Every Buick that passes me is red. Therefore, I have confirmed my hypothesis. All Buicks are red. But it's not true. That turns out to be one of the underlying drivers behind the vitality of science. One of the reasons that science is so powerful, because we can never prove things right, and we're always trying to prove things wrong. So, science, we confirm things rather than view things as truth. Science can accommodate rapid change. It values precision. And we relentlessly challenge our first principles. What do you mean that first principle is correct? I don't think it is. I'll do an experiment. I'll show you. And if I succeed in proving something wrong, a first principle wrong, boy, my name goes up in lights. That's a difference between a science way of thinking of things and an axiom basis of thinking of things. I see this as a real opportunity for integrated safety management. We move its basic principles and functions towards more of a science basis. We can harness the power of science in a much more powerful way than we have before. And we can come through breakthroughs. Now, I mentioned before that integrated safety management had some nice references to safety and cost, schedule, and product quality, some linkages in their principles. They're very loosely linked because they're axioms. I'd like to see if we can tighten up that linkage significantly, make it more quantitative. I think it's out there. I think we can do it. One of the things I have developed is a little flow chart here. You can't read probably some of these things, but I'd like to draw your attention to this section right down here where I talk about a research institute. There's a lot of folks in my business who believe they have the answers and the ultimate answers. That's why asking them, hey, you think you know what we need to do 50 years from now, 100 years from now, is a very intriguing question to ask. Often they pause and say, well, maybe I'm not so sure. The way to get to research, safety breakthroughs at this point, I think, is through research. I think we found the low-hanging fruit. I think the easy things we already know how to do. What's before us are real tough things. Think about the fact the vacuum tube was invented in kind of a one-person activity in 1907. But it took a research team and a systematic, disciplined research approach to develop the transistor. That was a lot harder. The two things I do not know, and this I guess I address to the engineering community, the faculty here, how interested the engineering community is, the academic community here, is in championing this type of research initiative. Those are things that I hopefully will come and get some guidance and advice here. I think there are people that are developing enthusiasm for this within the Department of Energy system. At the workshop last week, we had representatives from companies like Exxon who are kind of interested in thinking about these kinds of things for the chemical industry. This needs to be tied to the engineering schools, though, because our technology is such that many of these situations, there's an engineering answer that must be pursued. The other thing I don't know is whether, I can't prove it one way or the other, whether it's going to be worth the investment, whether we absolutely need these breakthroughs in order to survive as an industry. I'm a nuclear technology enthusiast. Unapologetically, I think this stuff is neat. I think our technology can bring many benefits to people around the world and do an awful lot more than what we've been able to show so far. And I think we're going to show that. But in the long term, without these breakthroughs, we have another significant event like a 3 Mile Island. I think we're going to have some traumatic outfall. So, from my point of view, safety breakthroughs are out there. I think they're waiting for us. We can shape the future of technology, but it's not going to be easy. This is not something that is going to be done overnight or without a real commitment. So what I ask everybody is, so what's it going to be? As we go forward, do we need the next generation of safety management to accompany the next generation of reactor design? We're going to stay with safety management vacuum tubes, or we're going to hop up to transistors and microchips. That's it. Thank you for your patience. If anybody is a glutton for punishment and wants to read more, there is a web address and there's more information and details and more research areas suggested in the web paper. Thank you very much.
Okay, we have time for some questions, comments. Well, everybody speak at once.
What if he'd been looking at Model A's of them Buicks, looking for black cars? They were all black, right?
Could I ever prove it?
Somebody might have painted one, right?
You got it. You got it. Yes, sir.
Don't people have to really accept these safety procedures for them to be implemented? I mean, on paper, everything sounds great.
Well, that's interesting. You mean the individual, the workers, and so forth?
Yeah.
You're right, and I think that's one of the frontiers, that we have some good ideas now, but that we could, with some research, find out a lot better techniques. Because if workers do not accept, see, one of the things that took me a while to figure out is that, frankly, people are not robots. As an engineer, I sit here and I'll write a great procedure for somebody out in the field to do something and do it very safely. But the factor you brought up, acceptance, is it something they can read? Are they paying attention? Are they ticked off because we forced them to do a lot of stuff they don't want to do? A lot of factors influence how somebody performs. And what this suggests is that we can come to much better quantitative understandings of those factors, and through those understandings, we're clever enough to find some much better answers.
Actually, a second question, but it also goes the other way, is that like sometimes when people do procedures, they're not very much aware of what's happening, you know, like in the field. So even
You got
it's not
it.
a question of being practical, accepted. It could not be implemented.
It's the whole package,
Yeah.
from the creation of the procedure to the implementation. See, and that's something that we only engineer bits and pieces of right now. What I'm talking about here is bringing that whole thing together and looking at the performance of the whole string from start to finish. Yes, sir. Yeah.
Dan?
Okay, yeah, I have a question about regulation, I guess. And I don't know, it's kind of a statement, maybe you can comment on it, but it seems to me that there's a perception that if you design an innovative safety procedure or technique, that many times you're still not going to be able to get rid of the old safety mechanisms that were in place because of the regulatory structure. So there's not as much incentive to, you know, if you can't replace the older, more expensive safety mechanism, why design a newer, faster, cheaper, better one, and then go fight regulators for years or whatever? Is that true? I mean, or is that just a perception?
Well, I think there's a lot of truth to that. I think that's a truth that is changing, if truth can change, because people are recognizing that simply focusing on safety and what you're comfortable with and what you can prove as a regulator isn't the final answer. And also, you know, as more people talk about, hey, wait a minute, why don't we make our technology more available so it can do more good to more people around the world? I think that begins to speak to people's hearts. And I think that will tend to influence it. But you're right, I think that is another very real factor that's out there, and one that we don't understand very well. After a while, if people feel that their great ideas are going to be ignored, they stop giving you great ideas. I mean, and then where are you? Okay. So that's very perceptive. I think that's very important. Anything else? Yes, sir.
It's pretty easy to understand technological breakthroughs, and there are lots of examples. What kind of examples can you give me for organizational or procedural breakthroughs that really change the way we do things?
Glad you asked me that. In the paper, I give a couple. That is a more difficult thing to describe, but one of them that has relevance to us, I've already touched on earlier. And that is, I think, there was a real breakthrough in nuclear technology that emanated out of Admiral Rickover in the Nuclear Navy. If you look at the influence that program has had on how we do nuclear business, whether some of the things people feel are not what they ultimately would like to see, or whether they're real champions and enthusiasts for that. No one can deny the incredible impact that it's had. I mean, I went back recently and looked at one of his papers that he wrote for General Public Utilities after the 3 Mile Island accident, his epistle to the nuclear business. Everything you guys need to do, by Admiral Rickover, right? And it was a fascinating thing to read, and a lot of his basic principles, they make a lot of sense, and they're with us today. So I would use that as an example of the discipline in his approach, the fact that he drove the engineering so people understood the basic engineering and had a certain basic technical competence at the working level. A whole bunch of his principles are wound into how we see effective nuclear operations today. And so I take my hat off to him. At the same time, there are limitations in his approaches. People have not explored those limitations as much as I think we should, because to find the breakthrough to the next level, you need to find out what the limits are. But I don't think most people would deny that he was a major influence on how we do business. I think he's a major breakthrough organization. Okay. Anything else?
Any other questions or comments? We do have refreshments for everyone down on the second floor, and we invite everyone to come down and join us for refreshments. The speaker will be down there. Before we adjourn, let's express our appreciation.